the New Year. It's the New Year day for the lunar year, and your presence attendance for this talk is the best present for me for the year of a snake. So I'm going to give the talk in the spirit of a snake to throw deep into PBL-cloud and their impact on aerosol-cloud interactions. So again, my name is Anqing Li, and this talk is mostly based on two former PhD students, Dr. Tianyong Su, who is currently a postdoc at the Lawrence Livermore National Lab, and current student Natalia Roland Halo. So here is the outline of my talk. I'm going to give a brief background, and then I'll go to introduce the two methods that we have developed for the detection of PBL, called PBL coupling. And then I'm going to talk about aerosol PBL interaction and impact on atmospheric thermodynamics. And that will lead to the study on the impact of a PBL cloud coupling on warm cloud as well as on deep convective cloud. So for many of us, we have seen this kind of thing quite often, especially if we've climbed mountain and looking back to the valley, or if you fly aircraft just shortly after taking off, you will see a layer of smoke haze like this. So this here is confined to the very bottom of the atmosphere. And that layer, of course, we know is aerosol. And why they are still there? Simply because they have some very stable condition over there that cannot break through this thin layer. So the distinction between the clean, crystal clear in the free atmosphere and the hazy boundary layer, that is basically the top of a planetary boundary layer, we simply call the PBL. So PBL has been known for a century, but really the problem and processes taking place inside the boundary is so complex that we still need a lot more investigation, which is also why PBL has been identified as one of the major uncertainty in the climate system that require a lot more study and the NASA decadal survey. So as a matter of fact, NASA has been trying to launch a new satellite mission to observe PBL. So as I said, if you swap down into the boundary layer, even though it's a very thin layer, it's just a couple of kilometers, but this layer has the most complex process going on, because this is the layer where the interaction between the atmosphere and surface taking place. And this is also the layer where the solar radiation is converted into many other type of energy. For climate studies, it is mostly the sensible heat and the latent heat flux. And this sensible heat flux is the source of heat that generates the buoyancy thermal energy to drive the convection and also turbulence, which effectively bring the moisture and energy from the surface layer into the atmosphere. And that layer is also the place where most of the aerosol are situated for the reason I just mentioned. So this aerosol will also serve as cloud constant nuclear, and that form cloud often near the top of the boundary layer. So which is why when we talk about aerosol and cloud interaction, this is the birthplace of that interaction taking place. So in this study, I'm going to highlight the major process that linking aerosol, PBL, and the cloud together. And this kind of a triangle interaction is the key for driving a lot of climate and weather system, especially convective cloud. So they are connected, for example, aerosol and boundary layer interaction through radiation effect, and aerosol cloud effect through the aerosol cloud interaction, and the cloud and boundary layer, they are through cloud PBL coupling. So I'm going to talk about PBL aerosol cloud interaction through all these interactions. Of course, won't have much time to go too much detail, but anyone interested can go some of the studies. So let's start with a relatively simple concept of the PBL aerosol interaction. As we know that aerosol generally located near the surface and attenuated with the height, but mostly they are confined to the boundary layer. So we see this this haze layer, brown haze. And this aerosol, this get so much amount of solar energy that reduce the heat coming down to surface. And this is the first relative effect. Secondly, a lot of aerosol have a certain concentration of black carbon or brown carbon, those kind of stuff. They absorb radiation and warm up the atmosphere. So you have the heated atmosphere, cold surface, you will have a stable atmosphere in the boundary layer, and which help to trap the aerosol. The more aerosol trapped, the more relative effect. So there is a positive feedback taking place in the boundary layer to really accelerate the buildup of aerosol inside boundary layer. As far as aerosol cloud interaction is concerned, boundary layer also important through this aerosol radiation interaction, and because that suppressed convection will certainly unfavorable for the cloud formation. And meanwhile, aerosol serve as cloud concentration nuclei will modulate the number of cloud droplets, and that is well known as a Toomey effect, so that same amount of water spread into more smaller droplets will reflect more solar radiation, so that's the Toomey effect. So in this study, we are going to talk about them in a little more detail. So that kind of concept sounds simple, easy to understand, but in the real world, the aerosol cloud interaction has been one of the most complex problems we are facing these days. And in 2019, I have a review article that survey studies around the world, and we look at different regions, and you can see the study showing very contrast effect. Okay, so first of all, this diagram showing the aerosol distribution, major aerosol plume, especially in the Africa dust and the biomass burning in the Central Africa and the Middle East dust and the Indian Ocean and the haze, and also haze in China spread across the Western Pacific. So this is aerosol that's distributed quite non-uniformly. Secondly, they are very much accompanied with the weather regime, which are also different. Monsoon weather is behind many of this, which is why we actually wrote a review article in Review Geophysics talking about aerosol monsoon interactions. And this, of course, it is go beyond the monsoon region. So overall, we found that aerosol can suppress or accelerate the cloud formation and depend on the weather system, circulation system, aerosol type, etc. So in general speaking, when you have less moisture and more the stratiform cloud, they suppress clouds. But when you have a moist region with more convection, they can invigorate the cloud. So let's now start with remote sensing method for determining PBL height and PBL cloud coupling. For this talk, I'm going to talk mostly about overland. Overland PBL cloud interaction is more complex because the surface is much more variable and stronger forcing from surface. And the coupling itself is thus more difficult to determine relative to coupling over oceans, which has been settled, and some studies have suggested that land is much more problem for us to tackle with. Okay, so as we know that boundary layer has most of the aerosol. So this aerosol has been served as a tracer of a boundary height. And in the traditional way, PBL is determined by radio sound measurement. Radio sound measurement provide the most accurate information about the boundary height, but they are only available twice a day in most stations, 4 times a day in some stations, and during the field campaign, we may have up to 8 times a day or even more. So that is the situation we are facing. So we cannot really use those radio sound to track the PBL evolution. But aerosol, because they trapped in the boundary layer, so we use that as the tracer using the LiDAR measure the extinction, we can estimate that. So in our early study by my former student, Dr. Sawyer, we developed an algorithm that can be applied to different sounding instrument, especially like airy, like micropulse LiDAR. And these different methods, they do have a difference, and because they rely on different signal, but overall, they have a gross agreement which help to track the evolution during a day and from day to day. However, when we apply those methods, by the way, that method has been used in the ARM for generating PBL for quite a few years. And those methods, when we look at it closely, we found that they usually work very well during daytime, especially during after noontime. But in the morning, especially in the early morning, they are often problematic. The reason is because the presence of residual layer of aerosol, they do not really change with thermodynamic condition. As we know, early morning, the PBL is very low. And as the sunshine is getting stronger, the PBL is lifted and getting higher. But in the early morning, the aerosol can stay there for a couple hours, even up to noontime. So as a result, if you use this aerosol as your tracer or proxy, you will get overestimated PBL. So to tackle this problem, we have resort to the meteorological data in the morning, and that will effectively calibrate this and give us a much more realistic dyno variation of the PBL. And we tested this method over different ARM mobile facility sites, and we found that they generally agree very well with the radio sound-based PBL height. And you can see this is the PBL. Oh, sorry. Oh, yeah, this is just published. And so now let's look into the concept of cloud PBL or surface coupling. And this coupling plays a very important role to the formation of a compact cloud grow out of a boundary layer. And the clear sky, we know that the boundary layer has a very constant virtual temperature. Above that, the virtual temperature decreases rapidly. For coupled cloud is just situated at the up boundary of the PBL. And in that case, the cloud is basically maintained by the constant effective transport of heat and energy, water vapor. So that will sustain the cloud development. But in the other case, when the cloud is well above the boundary layer, the cloud is decoupled from the boundary layer. So it's not so efficient to get water vapor and energy to help its growth. So in that case, cloud is more driven by the large scale circulation. So we have developed a method that can identify whether cloud is coupled with the PBL or not. So this coupling is very much determined by meteorology, especially the boundary PBL top height and the level of condensation, another meteorological variable. And in that case, we can simulate and also we can identify the coupling between cloud and PBL. And you can see they do well in different scenarios. So again, also we have tested this, and you can see coupled cloud, decoupled cloud, they are quite different. In general, decoupled cloud is well above the boundary layer, and they are behave very differently. And the cloud-based height is also systematically different for these two type of category. So we used the ARM SCP data over a decade. We have classified all the cloud as coupled cloud and decoupled cloud. If you look at the frequency of the two categories of cloud, and as well as cloud fraction or coupled cloud fraction, and we found that this frequency of coupled cloud happened mostly for those cloud-based height is relatively low. For example, less than 1 kilometer, most clouds are coupled. Above that, there's still some fraction of cloud are coupled, but the fraction is going less, while decoupled is going down, going more. And the fraction of a coupled cloud is even more clearly dependent on cloud-based height. Okay, the third part of my talk is about aerosol PBL interaction and impact on atmospheric thermodynamics. So using ARM data, we have classified the vertical distribution of aerosol concentration in 3 categories. One is decreasing with height, one is well mixed with height, and that's inversion. So the shade is basically all the profiles, while the blue curve is the mean and the standard deviation. And you can see aerosol do change with height, and they are generally speaking more in the lower atmosphere. And based corresponding to this distribution of aerosol, we can see the heating rate or relative forcing change dramatically among these three categories. So for the first case, when the aerosol decreases with height, in generally speaking, they are corresponding to very clean conditions. The aerosol is just in the lower part. While in the second category, well-mixed conditions, they are mixed all over the place inside the boundary layer. While in the inverse condition, the concentration is so strong, so is the relative heating as well. And that also helps explain the feedback between the aerosol PBL on the air quality as measured by PM 2.5. So what's the effect of this relative heating meaning to the dynamics? So we have looked at the buoyancy rate. The buoyancy rate, of course, is computed by this well-known formula. And that buoyancy is generally, of course, aerosol is increasing the heating of the atmosphere and cooling the surface, so it has a negative buoyancy, which means it's suppress the convection. So correspond to these three categories, you can see the buoyancy rate is rather small negative, while the well-mixed is moderate negative, and this inverse condition is very negative. So that means it has very strong effect to suppress the convection. Okay, given the importance of aerosol and PBL interaction, how do our models account for this effect? And we look at EIA5 and look at this analysis of the SCP region and also other places. We found that the PBL height agree very well from between the model and the observation and the clean conditions. And the polluted conditions, they start to do not so good with uncertainty about systematic bias about 30%. And the heavy conditions, they systematically overestimate the PBL by a factor of 2. So that's a very serious problem, and that can lead to many other problems associated with the PBL. And what's the effect of this on the entrainment? Entrainment is very crucial for cloud. So as we know, model used to use a very simple formula to determine the entrainment rate. The entrainment rate is basically determined by this ratio that's called entrainment flux divided by surface flux. So just use this, the entrainment rate is basically proportional to sensible heat flux, disregard the effect of aerosol. So when we separate the aerosol categories, you can see the entrainment does increase with sensible heat flux, but they do also differ considerably between clean conditions and polluted conditions. So that means the entrainment rate can be quite wrongly simulated in the model if you do not account for the aerosol effect. And based on that, we propose a new mechanism of aerosol entrainment coupling. So in the past, mostly we are concentrating on aerosol effect on surface heating. Aerosol, really forcing at surface has been the major topic. A lot of study has shown that. But actually in the atmosphere, especially in the boundary layer, the heating of the aerosol can be very dramatic effect. And that effect, the suppressed entrainment and suppress the buoyancy will suppress the PBL. As a result, we see PBL systematically higher in the clean condition than in the corrosive conditions. So this distinction effect of aerosol on the PBL may explain the systematic difference in the climatology of PBL height between the South Great Plain of US and the southern part of China. So this is over 10 years of data. And you can see that South Great Plain in US is about, on average, about 1.5 kilometer, while in the southern China, the PBL height is systematically less. By the way, this x-axis is also optical depth. So in the South Korea plane, there's not much systematic dependence on the aerosol loading, while in southern China, it is systematically decreasing with increasing aerosol loading. So that is a more clear illustration of the feedback. Why US does not have such strong feedback? Because the aerosol loading here is less absorbing than here. And this is further explained with the SCP further analysis. So using the AV sounding data, not real sounding, but inferred temperature profile and humidity profile, we identify all the inversion layer near surface and also inversion layer aloft. And we plot the statistical relationship between inversion frequency and aerosol number concentration. And we found that there's two curves. One is the inversion layer near the surface, one is the inversion layer aloft. You can see that near surface, inversion frequency systematically increase with aerosol loading. Okay, that we explained that. And likewise, the inversion frequency increase as a single scale below decrease, which means absorption increase. So more strong absorption has more inversion layers. So such effect of aerosol on the thermodynamics through the PBL interaction have a very strong effect on the cloud development, but there is also another effect, aerosol effect cloud, which is the so-called ACI, serving as cloud country nuclear. So let's look at what's the aerosol PBL interaction impact on warm cloud and precipitation. For a long time, we have been struggling to come up with estimate of the aerosol cloud interaction, the climate effect in terms of watt per square meter, how much this aerosol cloud interaction will affect this effect number. And there has been a systematic difference between model estimated and observation estimated. For example, illustrated in this study showing the two versions of the EC-HAM model and compared with observation estimation, the model systematically have a higher value than the model observation-based estimate. So whenever we have such kind of disagreement between model and observation, we usually attribute all that to the model problem. So what I'm thinking here is that indeed, model has a lot of problem to fix. And indeed, they have fixed a lot, and that has been improved consistently. But we also need to question how much reliance, how much confidence we can place on the observation-based. So this is the subject I'm going to talk. The reason I'm doubtful about the observation-based ACI is that we simply don't have a good handle on the estimation of aerosol-induced cloud number concentration. So the CCN is the number we need to get to approximate aerosol effect. But CCN has been hardly measured near the cloud bottom, except aircraft campaign measurement, which is why our friend Greg has done so much with aircraft, which is very important. But often we don't have such measurement. We rely on ground measurement of aerosol concentration or satellite-based aerosol loading for the entire column. So in neither case, they do not necessarily represent the cloud number concentration near cloud base. So this is the problem that will have impact on the aerosol cloud interaction induced relative faulting. So relative faulting due to ACI has been estimated by this formula with the three major quantities: liquid water cloud fraction. And this is one important factor that we realize, and more estimation has been done in recent years. And second effect is albedo of liquid effect. And third effect is somewhat relevant to this, but is sensitivity between the cloud number concentration to the aerosol number concentration or aerosol loading in general. So the question is, can aerosol proxy represent aerosol near cloud? So also the cloud PBL coupling will help answer this question. To tackle this problem, we have looked at the vertical profile of aerosol extinction from LiDAR, because LiDAR is the most rich data to denote vertical variation of aerosol, even though it is not the most ideal measurement of CCN, because it's proportional to the light scattering, which is proportional to the cross-section, which is not really proportional to the number concentration. But nevertheless, to the first order approximation, we use that as aerosol, as a CCN proxy. So we look at the correlation of the aerosol extinction at cloud base versus aerosol extinction near the surface, and also average inside the PBL, and also compare the aerosol optical depth for the column. So this is the SGP, this is Beijing, and we separate by coupled cloud and decoupled conditions. And you can see, in the coupled conditions, the correlation is pretty good, at least much better than decoupled conditions, and which the correlation is 0.2 or a little more than that, while this coupled condition is over 0.6 or near 0.5 in the AOD is concerned. So no matter in US or in China, same thing. So to look at this effect on the ACI, we basically use this different way of determining CCN or CCN proxy. And then we calculate the aerosol radiating by this, and by conventional method, we get this, and model get this, you have a big gap. But when we do the coupled and decoupled, you can see the number is different, and the sum of this will come up with very close to the model simulation, both in SGP and in Beijing. So the conclusion is that neglect of cloud coupling will result in underestimation of aerosol cloud interaction, especially for those that cloud is brought that is generated in the boundary layer. Now it's took a look of aerosol PBL interaction and impact on the deep convex cloud. So we all know this study by Daniel Rosenfeld et al., and that shows that aerosol can invigorate cloud by suppress the development of a cloud in the early phase. As a result, the cloud droplet do not grow big enough to precipitate out, and the hold on of the water will grow into the deep convex cloud, and at that time it will form into the thunderstorm, severe weather, and things like that. So this is the so-called invigoration. But of course, later on, many studies, especially by Ji and Fan, has shown that the invigoration is not limited to the mixed phase or cold cloud, but also happen for warm cloud, and warm cloud could even more than the ice invigoration effect. So to look at this aerosol effect deep convex cloud, it is definitely a lot more complex problem, because aerosol cloud interaction on deep convex cloud can be traced in every step of the development phase, starting from boundary layer, where the convection started, to the development from warm cloud into mixed phase, and then downdraft, etc. The layer, the entrainment, the condensation, etc. Every step there is an aerosol play a role. So if you want to take a closer look, feel free to read this paper. That's really deep dive into all the steps. Now we just want to draw your attention to my early studies showing that the cloud geometry in response to aerosol near surface. So the integration theory implies that we will have a more deep convex cloud, and we'll have a thicker cloud and heavy aerosol conditions than clean or light polluted conditions. So by analyzing 10 years data, we do find that cloud top height does increase systematically with aerosol amplification, but that increase is limited to a cloud that has very low cloud base. The reason for having this critical threshold of low cloud is because aerosol mostly in the local cloud. Secondly, coupling I showed you already is also for a cloud with low base. And as a matter of fact, if we look at this cloud by 3 layers, less than 1 kilometer is the strongest one, and above 2 kilometers, no dependence at all, and in between, also the effect in between. And this study, since published well over 10 years ago, it has been debated. So Adam Weber from PBL has looked at our analysis and reproduced our findings, which is good. We didn't do mistake. But he also found that the cape changes systematically with aerosol dynamic concentration. So he argued that it's the cape that drives the convection, which systematically change in the surface as a function of aerosol dynamic concentration, but underneath might be the cape that drives that convection. So if that were the case, indeed, it is not the aerosol effect. Okay, so how about this finding? How do we interpret basically the phenomenon is there? Anyone can get it. Now the interpretation or physical reasoning about this. So we look at this after we get a better understanding of the coupling effect. We sort out the cloud. In this case, we look at a lot more cases because we have many more years later separated by coupled and decoupled, and look at the same analysis, cloud thickness as a function of aerosol dynamic concentration. And you can see that the two families are separated clearly. Decoupled cloud, much weaker dependence than the coupled cloud. Coupled cloud is really showing the same strong dependence on aerosol dynamic concentration. So that is for decoupled cloud. We see look more clearly separated by cloud base height. Basically, reproduce our result, but separate looking from a different perspective in terms of coupling. Okay, so in light of what Dr. Adam finding that the cape could be the factor, so we limited the range of cape by small narrow region or interval, and from 0.1 here, 0.5, 0.3, 0.5, 0.9, and we can see that within each curve, the cape is very similar, okay? But it still shows strong dependence on the aerosol dynamic concentration. And additionally, this cape do have effect because as you can see, the curve systematically going up and the curve getting steeper. So this shows that it is both aerosol dynamic concentration and the cape that drive this cloud thickness to change systematically. But for decoupled cloud, we do not have such dependence at all. They are all mixed together, okay? Because aerosol will not likely to have any effect on these decoupled conditions. Now, let's look at the core of the question, which is cape and aerosol. Are they related? Answer is yes, but related for different reason and different consequence. And clear sky conditions, cape decrease with thin concentration, which is totally understandable because aerosol stabilize the atmosphere by scattering radiation back to space, by absorbing radiation, keep it inside the atmosphere, so they decrease. While for cloudy conditions, it's increased a lot, and that is the very argument of the aerosol invigoration due to latent heat release. Now let's take a closer look and see if we can reconcile the finding by Dr. Weber and us. And we look at the same cases as he showed in the paper, and we found that for this deep compact cloud, it is clearly showing that this is a well-defined deep compact cloud. Okay, well-defined here. And but the thing is, the difference between his analysis and ours, he used CAPE and aerosol in the middle of cloud, while we use it in ahead of cloud. The reason we use ahead of cloud because we do not want the cloud process itself tarnish or influence those numbers, because those are the environmental variable we should locate it before cloud even occurred. And for aerosol, it's even more so because rainfall can wash out the aerosol, even though it at the beginning, cloud is built upon CCM. So that means you cannot use those number concentration in the middle of cloud. So that's one problem. Another problem is when we look at all the cases they analyzed, we found he do not sample the case independently. For example, in this case, it is a well-defined one deep compact cloud, but he treated it as two cases. One cloud defined like this, which is right, but he even going from the middle of the cloud and find another as another cloud. And this is another case. You can find many are some cases like this. So this is violates the basic law of statistical analysis. You cannot duplicate your samples. And by accounting for this effect, we can reproduce his analysis like this. And but apparently, we just pointed out this is not right. By correcting this problem, we can get the result as we found. It's not a factor using the CAPE ahead of a cloud occurred. So this is kind of summary slide showing what is the complex interaction between the PBL, thermodynamics, convection, and aerosol distribution. And they are really a couple systems. Each of them can influence the other. Okay, so of course when we study them, we try to single out them, and then we have to account for them together. It is the this interaction or feedback that really make this problem interesting and more challenging. So in summary, we have found a way to determine PBL and PBL-cloud coupling, and this coupling between PBL and surface play a key role in both aerosol radiation interaction and aerosol-cloud interaction. So the unaccounted for such coupling will have a systematic bias in the estimation of aerosol-cloud interaction, and the coupling also play a key role in dictating aerosol invigority effect. And it is the C-CAPE relation that is not necessarily a matter of the covariability, but can also be a causal effect itself. These are just a few key references based on which of my talk. Thank you, and happy Lunar New Year. It's Year of Snake.